Okay, so now what we're going to do is now we're going to look at solving differential equations. Okay, and so this is where using power series is a powerful resource. Well, not resource, but a very useful tool in solving differential equations. So we're going to start with just a first order separable equation. So again, you may recall some of the stuff to solve these. So this is first order. You can see that it's a first order differential equation. It's also separable. And so we know that the solution to these types of differential equations is going to be of the form y equals c e to the x for some constant c. Okay? And so now, looking at this, we can see that we can get a power series representation. Okay, so the equation is easily solved using the techniques that we've been going over in the last several videos. Okay, now for most differential equations, however, we do not yet have the analytical tools to solve them. So power series are an extremely useful tool in solving many types of differential equations. And so in this technique, we look for a solution of the form of a power series. Okay, so what we're going to do is we're going to look for a power series representation where we can write this as a sum of c sub n x to the n for n equals 0 to infinity. Okay, so that's what we're going to do. Okay, now, and then we're going to have to determine what the coefficients are, okay, in order to make it work. So in this example, we're going to do a initial value problem, okay, and we're going to use an example of how we would do this. And so we're going to start with this, okay. So in this case, we're going to start with, in this example, we're going to start with the fact that y prime is, how do I want to do this? Equals y. Actually, we can disregard this. So we'll say y prime equals y, and we're going to say y of 0 equals 3. Okay, so that's what we're going to start with. Okay, so now the idea is we're going to suppose that there exists a power series solution like this. And again, it's going to have the form of c sub n x to the nth power. Okay. So again, just as before, we've seen this plenty of times. So it's going to be c0 plus c1. X plus c2 x squared, and so on. Okay. So the typical power series that we're familiar with. Okay, now, again, differentiating the series term by term, okay? So again, assuming that it exists, assuming that it's convergent, right? So we get y prime, right? So y prime equals what? It's going to be c1 plus 2c2x plus 3c3 x squared plus 4c4 x to the third, and so on. Okay, so that becomes y prime. Now, if y satisfies the differential equation, then what do we have? If this is true, then we have, let me start here, C0 plus C1x plus C2x squared plus C3, oops, x cubed plus C4, oh, let's just stop there. Dot, 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 is equal to C1 plus 2 C2x plus 3 C3 x squared plus 4 C sub 4 x cubed plus, and so on. Okay? So that has to be true. Now, using the uniqueness of power series, right? So if these are equal and these two series are equal to each other, then that must mean that what? That this is only going to be true if the coefficients are equal. So that means, therefore, what? C1 and C2 must be, or C0 and C sub 1 must be equal. So C sub 0 equals C sub 1. But that also means that C1 must equal C sub 2. Or no, I'm sorry. 2. C sub 2. And then C2 must equal 3 C sub 3. And so on. So that would be C3 equals 4 C sub 4. And so on. Now here's where the initial condition y sub 0 equals 3 combined with the power series representation is going to help us. Okay. So what do we get? So y sub 0 is equal to 3. So again, what happens? Y sub 0 is equal to 3. So all of these terms go to 0, and we're left with what? C sub 0 equals 3. Right? So then everything else falls apart, right? Or well, not falls apart, but you know what I mean. So now, but we know that C sub 0 has to equal 3 based on the initial value. And so now, based on this, what do we got? We know that C0 equals C1, which equals 3, right? C1 equals how do I, hold on. Let me think. Oh, here. Or no, I'm sorry. Let me do it the other way. That's what I want to do. So C0 equals to C 1 equals C sub 0 equals 3. Okay, that's what I want. Okay? And then C sub 2 equals what? C sub 2 equals 1/2 C1, C sub 1, which equals what? Three over 2. And then C3 equals what? C3 is 1/3 C2, which equals what? It's going to be 3 right? 3 over 3 times 2. And then C4 equals 1/4 C3, which is then going to equal 3 over 4 times 3 times 2, right? So now you should be able to be seeing the pattern here. And so if we keep going, then we get C sub n is going to equal 3. Well, let's do it this way. 1 over n c to the n minus 1, which then is going to give us 3 over n factorial. So this we can write as 3 over 1 factorial. This we can write as 3 over 2 factorial, and then 3 over 3 factorial, and 3 over 4 factorial, and so on. And so now we've got the coefficients. So therefore, what do we have? Well, if we put this together, then again, we know that the representation is given by that. And so we know that these coefficients are now given by this, so it's going to be 3 over n factorial, right? And we're done. So the representation, we can pull the 3 out because it's a constant. So this is going to be 3, and this is going to go from n equals 0 to infinity, and it's going to end up being x to the nth over n factorial. Now, this should look familiar. Okay? What is this series representation of? Right? So what we just did was we just said that y equals that series, right? Right? So we said y equals c sub 0, or excuse me, c sub n, right? Oh, well, yeah, let me just rewrite it. So c sub n, x to the nth, right? That's what we our assumption. We said, hey, let's assume that there exists, let's suppose there exists a power series, right? Well, guess what? Then we use the uniqueness of a power series to get our coefficients. in addition to the initial value, right? The initial value helped us there. And so now we know that y equals this, but this, the coefficients we just found, is this. So y equals 3, again, I'm just rewriting what I'm just reiterating. And my question again is, we should recognize that series. That's the Maclaurin series representation of what? E to the x. So that means y equals 3 times e to the x. So therefore the solution is y equals 3 to the x. So the solution to, so again, let's recap. So the solution to the differential equation y prime equals y, or the initial value problem I should say, the solution to the initial value problem of y prime equals y, given that y of 0 is equal to 3, is that. And, by the way, the thing is y of 0 does give us 3. And that's it. Have a great day.